Good day, class. Welcome back. In part 2 of this differentiation rules lesson, I promised you a quicker way to find the derivative of a function. And so here is the function that we were able to find the derivative of in part 1 of this lesson. And so notice here, I'm just going to unfold this very quickly, how in 3 lines, and depending on your skill set and depending on how you perceive this, your number of lines will vary, but you can quickly find the derivative of a function using differentiation rules. So don't let all this notation, much of what you see on this screen is just notation and order to maintain some sense of understanding, and you'll sort of adopt your style as we move through this. But it's much more simpler. It happens much faster once you learn the differentiation rules, and you will be able to quickly find the derivative of a given function as I have done here. So let's learn those rules. So sometimes you'll be asked to find the derivative of a constant. And so here's a notation type example and or a theoretical example. And so in theory, the derivative of c, or the derivative of a constant, is equal to 0. And so let's talk about the reason for that. Let's say we've been given y is equal to 5 and we're asked to find the derivative. Now, quite often we won't be asked to find the derivative of y is equal to 5, but very often in this class or in this study, you'll find that a constant will be somewhere in your function, and you're taking the derivative of various parts of that function, and then one particular part that turns up could be a constant. And so just I want you to know going in this thing that you'll automatically write that as 0, or the derivative, or determine that the derivative of that value, that constant value, is 0. The reason why: recall what derivative means, or taking the derivative or finding the derivative. We're talking about the slope of a line tangent. In some cases, we could talk about the slope of a tangent line. So if you have y is equal to 5, notice it might look like this on a graph, but what does a line tangent to a horizontal line look like? Of course, it's also going to be a horizontal line, and if you recall from your study of algebra, the slope of any horizontal line would be 0. So if you want to find the derivative of y is equal to 5, then I could write the notation here: y prime is equal to, or I could also write the same notation, d over dx of 5. Okay, so we're going to study this notation throughout this lesson, and then that is equal to 0. So no stress over the notation. It'll shake out for you quite well as we continue to pursue this. Then we have the power rule. And so the power rule says that if n is a real number, then we can differentiate in the way that we see here. So essentially we have x raised to the n, or some base raised to a power. And on the right side of that equal sign, it's telling us what to do with that base and that power. So notice how that power sort of comes down and multiplies by the base, and then that power also loses a value. So if I have my equation here, y is equal to x raised to the 9th, and I differentiate, we're calling all this is essentially notation to sort of guide us and tell us what we're doing, then that actually becomes the derivative of this equation becomes, or the derivative of this line becomes 9 times x raised to the 8th power. So let us consider the constant multiple rule. It's different than the constant rule we looked at a moment ago. And it says if c is a constant and u is differentiable, then we can do this. So remember, for this course, c is can obviously be a constant. We can notice that with no problem, but u is going to be differentiable. So we have this sort of caveat, but for us, it's always the functions that we're going to be working with in this course will always be differentiable. And if there's some quirk or something, we'll know about it in advance. So we can say, if we're presented with a problem such as this, then we can differentiate by just sort of pulling that constant off to the side, if you will, and sort of just dealing with it later. So that C sort of comes out, moves to the side, and then we differentiate the function that remains, or the piece of this function that remains. And so now we have, in our example, we have y is equal to -8 times x to the ninth. And if we want to find the derivative, remember we're looking for, in context, the slope of the tangent line, then we're going to find the, we're going to move that -8 off to the side, and we're actually going to differentiate the x to the ninth. And so in terms of manipulating, we're differentiating the entire function, but in terms of manipulating this thing, we're dealing with that x to the ninth, and that's what the constant multiple rule says we can do. So whenever you see the setup, just go ahead and pull that coefficient off to the side, and then we deal with the variable portion of it. And so now we learned about the power rule a moment ago. So now we know how to deal with that x to the ninth. We know that we can pull that 9 down in front of the x, and then we can lose one of the values. And so instead of not x to the ninth, we now have x to the eighth. And then, of course, we just simplify. So the derivative of this particular function is -72. Of course, we need to go back and multiply that -8 times 9. So we have, to simplify this, so we have -72 times x raised to the eighth. This is the slope of the tangent line. Now we have the sum rule. So the sum rule, this is another one that's very, very helpful. It seems very basic. When we look at it, we're really just talking about, we have the sum of functions, and if they're both differentiable, then they're differentiable separately. And so it just allows us to split them up and differentiate them apart from the plus that we have there with them. So essentially, if I have this, here lies a function, y is equal to -8x to the ninth plus 5, and then I can lay that out in function notation, or in using the notation for differentiation. And so I'll do that, but it looks really messy and very gaudy. But notice how I have, my initial indication that I'm going to differentiate the dy over dx, and then I have that is equal to d over dx of, and my function is there. And so the next piece, I'm just splitting them up and saying, okay, I'm going to differentiate them separately, these terms separately. The -8x to the ninth gets differentiated, and the 5 gets differentiated. And we dealt with those in the previous slide. So we know that -8x to the ninth becomes -72x to the eighth, and we know that that 5 goes to 0. So we're really just looking at the derivative of y is equal to -8x to the ninth plus 5. Well, we can easily identify the slope of the tangent line, which is going to be y prime is equal to -72/8 to the x. You may have assumed the difference rule works the same, and it does. Just like the sum rule, we can differentiate them separately, and our terms separately, and then come up with our first derivative. Notice the product rule. The product rule says if the function is differentiable, or the equation is differentiable, then we can use this formula if it is a product of two of factors. And so notice I have a product of two factors here, and I'm going to substitute those into my formula. So at first I'm just looking at my simple product of two factors, the 2x to the third power times the square root of x. And then to just sort of narrow this thing down, notice how we're saying that we're going to differentiate, and then we're going to take the derivative of, or we're going to look at the change in y over change of x, and we're going to take the derivative of our function in order to do that. And then we will use this product rule. So that's all this strip of wildness, it looks like at a glance, is saying. It's just the language of algebra that's telling us what we should do. And so we use those principles, the principles that we know about substitution, to apply them to this formula that we've been given. So we're very appreciative of the formula, and then we just plug in those values as we have them. And remember that you're going to differentiate, for example, the 2x cubed. And so notice how in y prime that becomes square root of x times 6x squared, because that is the implementation of that power rule. And so, and then in the next go round, that we're going to differentiate u. So now we need to take the derivative of the square root of x. And remember, you can change the square root of x to x raised to the 1/2 power. So think about that carefully when you're taking the derivative, finding the derivative of an equation, and then how's that going to look with it, even within the problem. We're really looking at all these various rules, and they continue to appear throughout, and we apply them. And then we just manage ourselves accordingly and make sure we're very neat, is usually, in my experience, what needs to be done. So when we complete this differentiation, or when we differentiate and simplify, we should end up with, in this case, a pretty simple representation of the slope of the tangent line. So y prime is 6x raised to the 3/2 plus x raised to the 5/2. Let's take a look at the quotient rule. Of course, we have that little caveat that says if u and v are differentiable, then. And so it looks kind of nasty, but honestly, it's not very difficult. It's just going to require us to stay focused and to really be organized and really be neat and have a pattern of operating. I would call it vertically, going, writing each line of your equation and following through each time. So in this example, or with this quotient rule, again, every equation or function that we're dealing with in this course is going to be differentiable. So we're looking at if this function is differentiable, then we can use the set of rules. And so at first, the set of rules looks pretty wild and crazy, but let's just take a look at how it appears if we have an actual rather than a theoretical equation. And so we have y equals 8x squared plus 5 divided by divided by x squared plus 8x. And so we just recognize u as the numerator and v as the denominator, and then we plug those in to our formula. And so just notice the first item here is simply saying we're going to differentiate. We want the derivative. I often write this as y prime. It just sort of lessens the work. And then next we have that we're taking we just have more notation. We're going to take the derivative of this particular equation. And then we actually take the derivative. Just pause this for a moment and just recognize how these items just fall into the pattern. And then you'll note that the only challenge here is keeping up with your signs and just managing those fundamental rules of algebra that you're very good at this stage. And so you'll be very good at this as well, and just remembering to stay organized.